go. We're going to look at our lab exercise in electricity and magnetism this week. We're doing a Wheatstone Bridge, and the Wheatstone Bridge is described pretty thoroughly in your lab manual. I encourage you to look through that. But we're going to do the experiment on a simulation on the computer this week, but we also want to talk just a little bit about this device, which would also allow us to perform a similar experiment in the real world. First, what's the purpose of a Wheatstone Bridge? A Wheatstone Bridge is designed to very precisely measure an unknown resistance. It kind of works like a balance does in terms of measuring mass. So for example, if you went to the market and you needed to measure out a certain amount of grain or a certain amount of gold, whatever it is you're measuring, you might have a balance. You might have a very carefully calibrated set of masses that you would place on the one side until the amount of produce on the other side balanced. And then you would add up the known masses on one side and you say they must be in balance to the unknown mass on the other side. So you're making a measurement by simply doing a comparison and trying to get the system in balance. Now in our circuit diagram, in the simulation, we have a power source down here. I'm going to turn off some of these additional indicators for the moment. Let's reset that. Okay. So we've got a power source down here, which is basically a battery. And then we have two paths that the current can take, through this or through this. And then what we've got is a known resistance. This would be a resistance which you knew very well, analogous to the known masses in a mass balance. And then these two across here are also going to be ones that are known. In this case, their sum is known, but you're able to adjust how much of the resistance is balanced to one side or the other. So in this case, we've got a total resistance in this path of 1,000 ohms. And if I push the slider more to the left, then I can make the left-hand resistance, for example, come down to around 100 ohms and the right-hand resistance closer to 900. This is what we'll call RB. That's what we call RA. Now there's also the bridge. The bridge is the connection between these two paths. And our goal for this lab is to adjust until no current is passing through the bridge. There, we got it. So we've got no current passing through the bridge. Now an ideal current meter offers very, very low obstruction. An ideal current meter has no resistance. Real world current meters do have some resistance. If we can set it up such that no current is flowing through the meter, it means the voltage at this point and the voltage at this point are equal. If this were high voltage and that were low voltage, current would flow up. If this were high voltage and that were low voltage, current would flow down. So by adjusting the ratio of the resistances here until no current flows, we're forcing those two voltages to be equal. It's very easy conceptually to understand when that occurs. It occurs when this ratio of resistances is the same as that ratio of resistances. So in this case, our left-hand resistance is 582 and our right is 487. So this is a little bigger than that. Likewise, this needs to be a little bigger than that. We might guess, in the range of 600, let's say. We can calculate that very easily on a calculator. We say 582.5 over 417.5, and then that ratio times 500 will give us this. And we expect, it's kind of in the ballpark of 700 there. Just eyeballing it. Let's click calculate resistance, and there we go. We've got 705, so that seems to be consistent with our estimate. We can also turn on voltage and current indicators, and we can see how everything changes as we then, let's take a new measurement, turn on our indicators, and we can see how everything adjusts as we move our sliders. So for example, you should notice that if this current is flowing up and this current is flowing in, then the sum of those two currents matches this current. In other words, 2.9 plus 2.4 is 5.3, and so on. And then we have things in balance when that middle current, the current through the bridge, goes to zero. So the last thing I'll show is a comparison of how this device works relative to a real-world system, which can perform a similar measurement. But this is a nichrome wire across there. The wire has some resistance, and the resistance depends on how long the wire is. So if you have a longer wire, it has more resistance. You have a shorter wire, it has less resistance. So what one would do is perform a function identical to what's happening here in the simulator by sliding the joint at which one makes the electrical connection. So if the joint is in the middle, then the ratio of the resistances is 1. If the joint is over here at 25 centimeters, then this is 3 times the resistance of that. So one moves this back and forth until no current flows through the bridge, And at that point, one knows that this resistance compared to that resistance is the same as the unknown resistance compared to the known resistance. So again, in summary, basically what we're doing is just creating a balance, and this balance allows us to measure with very high precision an unknown resistance in terms of other resistances that we know. Last thing that's kind of interesting is we don't actually need to know the resistance of the wire. All we need to know is that it is relatively uniform, because all that matters is the ratio of the resistances. So as long as the wire is relatively uniform and it's manufactured to be along its length, then what's relevant is the ratio of the left hand to the right hand resistance. And we can get that simply by comparing the lengths along the ruler. So that's this week's lab.